Hi everyone, my name is Roshi Wang, a master student from Imperial College London. It's so pleasured to get this chance to share our work. Our work is real-time surgical environment enhancement for robot-assisted minimally invasive surgery based on SuperResolution. As we know, minimally invasive surgery has the advantages like less trauma, less pain, and faster recovery. Both patients and surgeons can benefit from it. However, it also brings challenges and limitations. In minimally invasive surgery, surgeons cannot see the organs or tissues inside the patient's body directly like in open surgery, but need to look at the images on a monitor which are captured by the laparoscope inserted into patient's body. This indirect visual feedback would also cause limited field of view. In addition, surgeons cannot control the laparoscope by themselves because they need to do operations. In this case, a camera assistant is required to control the laparoscope under surgeon's instruction to provide surgeons with their desired view. So, another limitation is the low tacit cooperation between surgeons and assistant. In some extreme cases, surgeons' operation may fail due to the belated response of camera assistant. The problems we want to solve is, first, the limited field of view caused by zooming operation. When the laparoscope performs zooming in operation for a certain region, surgeons will lose original field of view but focus on a specific point, which may lead to incorrect operations. And second, low tacit cooperation between surgeons and assistants. The unsmooth cooperation between surgeons and assistant will impose negative effect to the operation. In order to solve these problems and build an intelligent robot minimally invasive surgery system, we need to accomplish following tasks. The first is design a method to provide real-time visual composition information when the laparoscope is zoomed in. The second is enable the system to learn and predict surgeon's operation and do corresponding response automatically without requiring surgeon's command. Therefore, the pipeline of the framework is first, a region of interest is initialized by surgeons and then tracked by a real-time object tracking method. Second, a context awareness method is applied to predict surgeon's operations, and the predicted results will determine the upscaling factor of the region of interest. And third, we will select the upscaling factor according to different operations for super-resolving the region of interest. The SuperResolution method is designed to increase the resolution of original images while obtaining better visual quality compared with simply magnification. Two primary modules utilized in this paper are the context awareness module and the SuperResolution module, and we will only focus on the SuperResolution part in this paper. The context awareness part is presented in another paper of ours, which named Surgical Gesture Recognition for Robot-Assisted Minimally Invasive Surgery based on Bidirectional Multilayer Independently RNN with Explainable Spatial Feature Extraction. In summary, the main contribution of this paper include propose a GAN-based real-time multi-scale video superresolution method, solve the checkerboard pattern of artifacts in deep learning-based superresolution approaches, and build a framework to estimate the region of interest and provide automatic zooming function with high-quality images. And this is the architecture of the generator network in our GAN-based superresolution model. A multi-scale structure is designed to generate images with different resolutions because the region of interest needs to be super-resolved to different resolutions according to surgeon's operation. There are two branches in this network. The top one is for feature extraction and the bottom one is for image reconstruction. In the feature extraction phase, residual dense blocks are employed at each scale to make better use of the features and enhance the transfer of the features. A residual connection is additionally added to each scale to ensure the representative ability of the model. Specifically, 1x1 convolutional kernels are used in residual dense blocks to increase the training and inferencing speed. The dense connection enables the input of each layer come from the output of all previous layers. Each layer has direct access to the gradients from the loss function and the original input signal, leading to an implicit deep supervision, thereby improving the performance. In the image reconstruction phase, images with different scales are reconstructed in the Laplacian pyramids nature. To discriminate the real images from generated images, we trained a discriminator network. This is the architecture of the discriminator. Here, I borrowed the idea from relativistic discriminator, which estimates the probability that the real image is more realistic than the fake one, instead of estimating the input image is real or fake. Therefore, the discriminator is encouraged to estimate the real image is more realistic than the fake one. As for the loss function, the pixel loss, the content loss, and the adversarial loss are combined with different weights to train the model. To better handle outliers, L1 Charbonnier loss is employed to calculate pixel loss and content loss. To further improve the visual quality of generated images, temporal information are extracted and combined with the fully extracted spatial features to reconstruct images with high-frequency details. Therefore, we designed a recurrent video SuperResolution framework. This framework uses the previously inferred high-resolution image to super-resolve the subsequent frames. Specifically, first, we compute the optical flow between the frame t-1 and frame t. Then, we perform the space-to-depth transformation to the previous super-resolved image to map it to low-resolution space. This is because that we want to improve the inference speed of the model. Finally, we concatenate the flow, the mapped previous result, and the current frame, and input them into the generator. The recurrent nature also reduces the computation cost. To further improve the speed of the algorithm, a knowledge distillation method is designed to compress the model while maintaining its performance. The general strategy of transferring the knowledge is to let the student model to mimic the intermediate results of the teacher model. The residual blocks in the generator network are divided into several sections by their spatial size to enable the student model to learn not only the intermediate results but also the process of the solutions. We define the distilled knowledge by the features extracted from the first and last layer of each section and the VGG feature of the final output. There are two stages in the knowledge distillation training procedure. In the first stage, we extract the distilled knowledge from the teacher model to train the student model. And in the second stage, the pre-trained student model is fine-tuned. Here we can see a strange checkerboard pattern of artifacts in these images. This artifact tends to be more prominent in images with strong colors, like the real surgical images, and it appears in many super-resolution methods when the upscaling factor is bigger than 4, such as sRGAN or eSRGAN. Experiments verified that this checkerboard pattern of artifact is caused by the transpose convolution, because the transpose convolution can easily have uneven overlap when the kernel size is not divisible by the stride. Well, in principle, the network could carefully learn the weights to avoid this artifact, but it will sacrifice the model capacity and is hard to achieve. And in fact, models without uneven overlap can also cause similar artifacts. It's tricky to avoid this artifact completely when using transpose convolution. Therefore, we use upsampling plus convolution to replace transpose convolution to solve this problem. Then is the super-resolution results. The video shows the comparison between the input low-resolution images and the generated high-resolution images. The inference speed of the SuperResolution method here is around 20 frames per second. Then we use the JIGSAW dataset to evaluate the proposed framework. The region of interest in the yellow box is tracked. The surgeon's operation is predicted and shown on the right side, and the region of interest is superresolved by different upscaling factor according to the predicted operation and shown on the right screen. Finally, in conclusion, we constructed a whole framework for surgical environment enhancement to provide surgeons with better assistance in surgery. This is our first step in trying to build an intelligent surgery system. At this stage, this exploratory work achieved a fully automatic surgery assistance system with higher visual quality and faster processing speed. Specifically, the system is able to recognize and predict surgeon's operation and perform corresponding response, which is providing high-quality visual feedback while maintaining sufficient field of view. In the future, we will collect more data for thorough evaluation of our framework and make optimization to the solutions. Also, we will try to deploy the framework onto real surgical robots for user study, which is delayed due to the COVID-19. Thank you for listening.